Question 8. The curve has equation y equals 2x cos of 3x and 3x squared minus 4 lots of sine of 3x. We want to find dy by dx, giving our answer in the form mx squared add n cos of 3x, where m and n are integers. So there is going to be a lot of chain rule and product rule differentiation here. So let's break it down. So let's say f of x is 2x cos of 3x. Okay, so let's find df by dx. Okay, so we're going to need to use the product rule and the chain rule in half of that. So let's differentiate 2x. So that gives us 2. And then we don't differentiate cos of 3x. And then we don't differentiate 2x. But we do differentiate cos of 3x. So by the chain rule, the derivative of 3x is 3, and the derivative of cos of x is minus sine of x. So we're going to get minus 3 sine of 3x. So that gives us 2 cos of 3x minus 6x sine of 3x. Okay, now let's call g of x 3x squared minus 4 sine of 3x. So g of x is equal to 3x squared minus 4 times sine of 3x. Now you could, of course, here expand the brackets out if you wanted to. I'm going to do it though all in one go using the product rule. So dg by dx is going to be, well, the derivative of the bracket times sine of 3x. So that's going to be 6x sine of 3x. So that's nice, that's already going to cancel with something up above. And then we do the bracket times the derivative of sine of 3x. So again, the derivative of 3x is 3. The derivative of sine of x is cos of x. So this is multiplying 3 cos of 3x. So let's write that as 6x sine of 3x, and let's add 3. In fact, let's let the 3 inside of that first bracket, so we get add 9x squared minus 12 cos of 3x. Okay, now altogether dy by dx is df by dx and dg by dx. So dy by dx is 2 cos 3x minus 6x sine of 3x. So 2 cos of 3x minus 6x sine of 3x and 6x sine of 3x and 9x squared minus 12 cos of 3x. Okay, so in the middle there, the sine terms cancel out, which is really nice. So dy by dx is 2 cos of 3x add 9x squared, so let's expand the bracket, so add 9x squared cos of 3x minus 12 cos of 3x. So everything's got a common factor of cos of 3x, so that's good. Okay, now 2 cos of 3x minus 12 cos of 3x is minus 10 cos of 3x. So we've got 9x squared minus 10 lots of cos of 3x. Cool. Okay, then for part B, we want to show that the x-coordinates of the points of inflection satisfy the equation cot of 3x is equal to 9x squared minus 10 over 6x. So at points of inflection, the rate of change of the gradient is 0. So that means d squared y by dx squared is equal to 0. So we should start by writing something like that. So at points of inflection, d squared y by dx squared is equal to 0. Now we know from part A that dy by dx is 9x squared minus 10 cos of 3x. So what we need to do is differentiate that. So d squared y into colour, d squared y by dx squared. So again, we are using the product rule. So if we differentiate the bracket, we get 18x times cos 3x. And then if we differentiate cos of 3x, we get minus 3 sine of 3x. So we can write this as minus 3 times the bracket times sine of 3x. So at the points of inflection, we want this to equal 0. So 18x cos of 3x minus 3 lots of 9x squared minus 10 lots of sine 3x is equal to 0. Now we have a common factor of 3, so let's divide that away. So we get 6x cos 3x minus 9x squared minus 10 over times sine of 3x is equal to 0. Now let's move that second term onto the right. So we get 6x cos 3x is equal to 9x squared minus 10 times sine of 3x. Now if we divide by sine of 3x, 6x cos 3x over sine of 3x is equal to 9x squared minus 10. Cos over sine is cot, so 6x cot 3x is equal to 9x squared minus 10, and then finally divide through by 6x, so cot of 3x is equal to 9x squared minus 10 over 6x. We've proven it. Let's put a cheeky little QED. Quite enough done.